So the test will be like the exam will be like last time, right? It would like all the other exams, um, about 25 or a little longer, right? Because it's cumulative. So about 25 questions and about 4 problems, right? So there's a couple of things that you should know already, right? So I mean, there's a couple of definitions that you should know, right? So for example, right, we should know what weight is, right? And weight is a force, right? And it's so it has magnitude and direction, and it's equal to the mass times the acceleration of gravity. Right? And we said that so it's equal to m times g, right? Okay. And we said that um, your weight depends on what planet you're closest to, right? So your weight can change as you move through the different through the universe, but your mass, right, is a scalar, so it doesn't have a direction, right? And your mass always remains the same. No matter where you are in the universe, unless you start moving close to the speed of light. So we won't worry about that, right? You move close to the speed of light, your mass starts to increase, right? But it's always looks the same. So, for example, if your mass on Earth, right, an adult person on Earth is somewhere around 60 kilograms, right? Okay. And then your weight on Earth would be 60 kilograms times 9.8 meters per second squared, right? Or about 588, right? Okay. And the units are newtons. So if you want to know what the weight is, it's the mass times acceleration, right? So usually in the United States, we buy according to weight, but we buy it in pounds, right? And in other countries, they use mass, right? So they get it in kilograms. So this is on Earth. If we're on some other planet, right, your mass would still be 60 kilograms, right? That's the good thing about mass. It can't change anywhere you are, right? But let's say G for this planet is equal to 10 meters per second squared, then your weight would be 600 newtons. This planet would be actually larger than Earth, right? So it had stronger gravity. So the difference between the two is that one of them never changes, right? So it's a good quantity to measure. And this has to do with the force of attraction of whatever planet you're closest to, right? And it will change. We also talked about density. And we usually use either capital D or a lowercase letter rho, right? And we said this was the mass per volume. So for instance, if we had ice cream mix, right, it would have some density, right? And we would figure out its mass and divide it by the volume, right? And let's say it's just the volume of the mix, right? If we made ice cream out of it, so let's say we had 1.5 gallons of ice cream. From the 1 gallon of mix. Right? We said in that case, we have the volume of the product. Right? Is now larger. So it's about 1.5 times the volume of the mix, right? Okay. So the volume increases. However, it's still the same mass, right? Okay. So it's still the same mass. So that means the density of the product is going to be less than the density of the mix, right? So he said density is a measure of kind of how thick something is, right? So it's how much mass there is per volume, right? So if we had brick, and a styrofoam brick the same size, and let's say this is V1 and this is V2, right? This would be much less, I mean, the density would be much less for the styrofoam, right? So let's say their volumes are the same, but their densities of the styrofoam brick would be much less than the density of the actual real brick, right? Okay. So we talked about weight, we talked about mass, and we talked about density, right? Okay. We also talked about so we also talked about temperature. And we said that temperature is a measure of the average kinetic energy of the molecules. So the higher the energy, the higher the temperature, the higher the average kinetic energy of the molecules, right? And we said kinetic energy is energy due to motion, right? So kinetic energy is energy due to motion. And if you wanted an equation for it, we could say that it's equal to 1/2 the mass times the velocity squared. Right? So as we heat things up, they start vibrating and translating, which means moving in a straight line, rotating. All these molecules start adding energy to it. So one calculation, right, might be that you have to figure out what the weight is, which is just the mass times gravity, right? We also talked about um, three temperature scales, right? And we said the first one was degrees Fahrenheit, and we had degrees Celsius, and we had Kelvin, right? Okay. And we said that both Fahrenheit and Celsius are based on the freezing and boiling point of water. At sea level, right? Okay. So it 1 atmosphere of pressure and right. So that was important. We said the Kelvin was based on um, the constant volume gas thermometer. Right? Which isn't very intuitive, right? If somebody really forced you to say what it was, you could say that it's a measure of the kinetic energy of the molecules. Where at Z0K, molecular motion stops. Right? So that's kind of a strange thing to say, but so the idea is that if we model atoms like this, and don't forget, this is just a model to try to explain some of its behavior, right? We model it as two atoms stuck together by a spring. If you heat them up, they start vibrating a lot. And if you slow them and if you cool them off, they start slowing down, right? Is that okay? So with these temperature scales, we said that freezing is 0 degrees C at 32 degrees Fahrenheit. And we said boiling was 100 C and 212 degrees Fahrenheit, right? And we said it would change though um, um, as the pressure changed, right? So if we went up in the mountains, boiling point would lower, right? And if we went down into a mine, boiling point would increase, right? And we said that in this case, so if the boiling point decreases, then the food doesn't get as hot and it takes longer to cook, right? And if it increases, then it cooks faster, right? So that's the concept behind a pressure cooker. We'll close it up and if the pressure increase, in which case the boiling point increases and your food cooks faster, right? That's what the idea behind a pressure cooker is. Right? And we said we could, so this is the next calculation you might have to make, right? We said that the temperature in Fahrenheit is 9/5. The temperature in Celsius plus 32. And the temperature in Celsius is 5/9. The temperature in Fahrenheit minus 32, right? Okay. So there's bound to be two questions about that, right? So first, if we're given that the temperature in Celsius is 20 degrees C, right? Okay. I'm sorry, I keep using 20, so let's use 25. So it's 25 degrees C, right? Then the temperature in Fahrenheit would be 9/5 of 25 plus 32, right? Is that okay? Right? And then you can plug it into your calculator, but this one's pretty easy, right? 25 divided by 5 is 5, right? Times 9 is 45. And 45 plus 32 is 77, right? So that'd be 77 degrees Fahrenheit, right? Or if we had, say, Fahrenheit was 100 degrees Fahrenheit, we wanted to know what that was in Celsius. That's 5/9 of 100 minus 32, right? So I was trying to think of one that I could do in my head. So 100 minus 32, right? Times 5 divided by 9, and we end up with about 37.77 degrees Celsius, right? Any questions about that? Okay. All right, so there were a lot of definitions that you needed to know to start out with, right? And then we went on from there. Okay, so sorry, 1 second. So if we look at what- bless you. So I was gonna say is that you probably hear this in your sleep, right? Got the definition of ice cream, right? Ice cream is a food produced by freezing, stirring, pasteurized mix consisting of one or more optional dairy products, right? Okay, so I'm sure there'll be a question about that. So the important things here is that freezing, stirring, and pasteurized and dairy, right? Okay. Everything okay? And we said that it went on to say that if we look at part two of that. That ice cream contained not less than 1.6 pounds of total solids per gallon, right? And not weigh less than 4.5 pounds per gallon, right? Okay, so and you can make up some percent of the solids, but that's the main thing, right? And the reason that this is done is why? Why do they want to measure the weight of the ice cream? Yeah. Yeah, so it's a quality issue, right? So they're saying that you can only have 100% overrun, right? Okay. So what this statement says, so you should know the statement, right? That it contains not less than 1.6 pounds of solids per gallon, and it weighs not less than 4.5 pounds per gallon, right? And it's before you put anything in, but that you don't have to worry about that, right? So in this case, what it does is that it's a quality issue, right? Okay, and what it does is limit the overrun to 100%, right? So it limits the overrun to 100%. And what that means is that you can make 2 gallons of ice cream from 1 gallon of mix. Right, so you can make 2 gallons of ice cream from 1 gallon of mix. Any questions about that? Okay. And we defined overrun be equal to what? What we define.
Product divided by what?
So product minus mix. Okay, and don't write that the rest of it down yet, right? If we did product minus mix divided by product, that would be the percent of air that's in there. Is that okay? That would be the percent of air that's in there, and that's what you would normally think that they want to know. But instead, right, we'll divide it by the mix, right? Okay, and a good way to remember is if we have 2 gallons of ice cream minus 1 gallon of mix, that's 1, right? Divided by 1 gallon of mix, we get 100, right? Okay. If we were to do it the other way, and that means it's 50% air, is that okay? Right? So I know normally you think they want to know the percentage of air, but they don't, right? What they're saying is that the volume of product minus volume mix, and this gives us 100%, right? And if there's 100%, it means that you have 2 gallons of mixed product for 1 gallon of mix. Is that okay? All right, so any questions about that? Okay, so that's probably the last equation that you have to do, right? If I remember correctly. After that, we started talking about the energy that's found in ice cream. I'm sorry, first we talked about composition, right? And if we look at the composition of ice cream, we said that right, we had different types of ice cream. So for example, we had plain old ice cream. Then we had frozen custard, and frozen custard meant that it had eggs in it, right? And it's also sometimes called French style, right? We also had reduced fat, low fat, light, and non-fat, right? And we'll talk about that in just a second. Then we had frozen yogurt, which isn't milk, which isn't ice cream, right? So that's not ice cream, but that's okay. And we had sherbet, which also isn't ice cream, and Melorine, which is if you take your ice cream mix and remove some of the good expensive milk fat and you replace some of it with vegetable oil, right? Some kind of vegetable oil that comes into Melorine, right? Okay. And we had one more, and that was Turkish ice cream. And if you remember, that had scallop flour in it, right? And that comes from orchids, right? Okay. So that was a type of ice cream that's really thick and it comes from orchids, right? So here's some examples of the overrun, right, that are in the slides, and you can take a look. So if we said we look at the backbone of ice cream, right, it's this sugar water. So it's about 80% water and about 20% sugar, right? Okay. And about 5% of that sugar usually comes from lactose, right? So roughly, most ice creams, there's, like we said, the backbone is the sugar water, and it's just sugar and ice cream and water. So what's contained in the ice cream? We said there's milk fat, right? And we said that this was the natural fat of milk from which butter is made, right? And sometimes it's called butter fat, right? So we have that in ice cream. And then we had milk solids not fat, right? And we said milk solids not fat were anything solid that wasn't fat, right? So we said milk solids not fat or serum solids. Right? We said that they would be everything but water and fat. Okay, so it's everything but water and fat. And we said it was protein and lactose. And we said lactose was milk sugar, right? Which chemically is just like any other sugar, right? Just that it's coming from milk. And ash. And we said that this ash was vitamins and minerals, right? So these are things you don't get energy from, but they're necessary for your body to be able to convert food into energy, right? Okay. So really, that's what we're trying to do. We're trying to eat something and take energy from it and build up our bodies and do work and stuff like and think and stuff like that, right? So, so that's what we're left with. We also talked about the fact that you're going to add sugar, sucrose, which is just normal everyday table sugar. And if you remember, it comes from sugar cane and sugar beets, right? Okay. So it comes from sugar cane and sugar beets. And all you do really is just boil the heck out of them, right? So you throw them in water, just keep boiling them, boiling them, boiling them. And then what you're left with is sugar, right? Okay. There's also, so that's sucrose. There's also corn syrup solids, right? And some people think that you could taste the difference between them, and some people probably can, right? But also, this is usually cheaper, right? But it has kind of a bad rap, right? So it's chemically similar to the other sugar, and but right. So how do they make that? They throw corn in with some water and boil the heck out of it until they get a sugary syrup that's left, right? So corn syrup's usually cheaper, right? And like I said, some people think they could taste the difference between it. So we won't have like a lot of questions about it, but we should know that stabilizers are put in there to maintain the physiochemical state of the food stuff, right? Okay, in essence, it's made so that ice cream will keep its structure for a while, right? So it doesn't, as soon as you take it out of the refrigerator, melt into a pool of mix again, right? Okay, so it tries to help you maintain that. It also helps to things with things like, you know, you make it at the factory and then you put it on a freezer truck and then you drive it to the store, and then it comes out of the truck. And for a few minutes, it's on a loading dock somewhere and it's getting a little warm, maybe a little bit of it melts, right? So it'll help stabilize that and help it keep it in its structure, right? And it stays out, and there's very little of it, right? There's only a tiny percentage of it. And also we had emulsifiers, and that's to keep everything well mixed, right? So for instance, the eggs that you put in make a good emulsifier, right? They help keep everything well mixed. Don't forget, we don't freeze all the water in ice cream, right? Or else it would be like an ice cube, right? So the amount of water that actually turns into crystal ice depends on how cold we make it, right? Okay, so that means that part of that ice cream is liquid, right? So things can move around in a liquid, right? So the emulsifiers and stabilizers are to keep it so that that doesn't happen. Is that okay? Right? So really, if we look at ice cream, right? What we have is a liquid dirt, right? Which is water and sugar. And we threw vanilla in there too, right? Okay, so this liquid part is water and sugar, and then there's ice crystals. And the size and amount of ice crystals there are depends on how cold you make it. So unlike water, that once it hits 0 degrees C or 32 degrees Fahrenheit, it'll not change its temperature until it turns into until the whole thing's frozen, right? That's not true with ice cream, right? So with ice cream, as you get colder, there's more ice crystals, right? Okay, and the size and shape of these affect the quality of the ice cream, right? Okay, so if they're too big or too small, you won't have good mouthfeel for it, and it won't melt consistently. Is that okay? And then you have fat globules, right? And the protein isn't shown here, but you have some protein, right? And one of this. So why is these white spaces here? For the air that you whipped in, right? So that's for the air. So don't forget, ice cream can be up to 50% air, right? And about 30% ice and about 15% sugar and water and about 5% fat, right? Okay, so that's roughly the composition. If you want to go a little bit closer, right? Then we also have a little bit of protein, some mineral ash, some stabilizers, some lactose and milk salt, right? But the mix is mostly water, right? Okay, just like milk is mostly water, right? So there's just general questions about this, right? Not specific temperature, amounts or anything like that. Oh, for the stabilizers, or I'm sorry, the emulsifiers. Don't forget, the way these work is they have these chemicals that have hydrophilic, water-loving part, and a hydrophobic, water-fearing part, right? And what happens is the hydrophilic part goes to the outside, and the hydrophobic part that doesn't like water, tries to embed itself into the protein molecules, right? Okay. So, and then they coat the protein and kind of help keep it well mixed, right? Okay. Otherwise, what'll happen is, the proteins will all try to glob together because they don't really like the water either, and the fat, right? Okay. And what'll happen is they'll try to glob together and make big globules so that most of their stuff is in the inside, right, protected from the water. So this is what emulsifiers do, right? So the words hydrophilic and hydrophobic, you should know what they are, right? But it's water loving and water fearing. And what happens is it drives the water fearing part, the part that doesn't like water, into the molecule, right, of fat and protein. So don't forget this table that you have, right? Table 2.1 in your book, right? And so there could be questions about like, what's milk fat and maybe what's the function of milk fat and what's its limitations, right? And we said that, right, so really rich ice cream has fat in it, right? And more fat than normal. You can't overdo it, right? Listen, you can't get so much fat in there that like it's just too disgusting, right? But so you have to be careful about that. And also the fat makes it so it doesn't whip as well, right? So you're trying to add air and the milk fat will try to fight it. But it is what gives you a lot of the flavor, right? So the milk fat is giving you flavor. And it also gives you some of the mouth feel, right? So it lubricates and insulates your mouth and makes it feel good. Right? Then we have non-dairy fats, right? They are cheaper, so that's good. And sometimes they can add some good structure. So for instance, if you're making popsicles, you know, that are made of ice cream, you might want to put a little bit of non-dairy fats in there because it'll help maintain the structure, right? Because if you think about it, you can't just like cut out a section of ice cream and stick it on a stick and it would work, right? Okay, you have to modify it a little bit. So usually reduce the overrun and add a little non-dairy fat to it, right? Okay. And milk solids, not fat, right? They improve the body and texture and promote overrun, right? Okay. However, if there's too much of them, it can taste salty or sandy, right? Or feel sandy or taste salty. And then we already talked about the sugar and the corn syrup and the stabilizers, right? They add sweetness, and sugar is more expensive than corn syrup, but not by much, and things like that, right? So any questions about that? So then we talked about the different types of ice cream, right? And we said, for example, reduced fat has 25% less fat than the reference ice cream. So if you're selling a vanilla ice cream and you have another vanilla that's called reduced fat, it just has to be 25% less than your regular vanilla ice cream, right? If it's light, that means it has to be 50% less fat. And if it's low fat, then they actually start going down to the making actual measurements, right? So don't forget those first two, reduced fat and light, just means 25 or 50% less for your reference. So if you buy like Friendly's ice cream and Friendly's light, and you buy Haagen-Dazs ice cream and Haagen-Dazs light, their lights might have, one of the lights might have more calories in it, right? Okay. With the low fat, it actually, then you kind of define, there's no more than 3 grams of milk fat per 4-ounce serving, right? So for low fat, that's what it means. And for non-fat, there's less than 0.5 grams of milk fat per serving, right? It's really hard if you take out all the fat you have to add something back in, right? Okay, so, okay, any questions about that? And then we said that, oh, we also talked about gelato, right? So this time we didn't get a chance to taste it, but it is typically lower fat, lower overrun, right? Higher sugar, right? So gelato is usually, and it's also sometimes called Italian style ice cream, right? So lower fat, lower overrun, higher sugar. And one of the sources of the sugar is that a lot of it is fruit based, right? So strawberry and things like that. And and of course that fruit has sugar in it also. So they add more sugar and they put fruit in it. So there's a lot of sugar. And then we said Turkish ice cream, it's ice cream that's so thick that you actually have to cut it with a knife and fork, right? So that's how thick it is. And it has sellout flour, right? And it comes from the orchid root. So don't forget, there's only two things you can eat from the orchid. One, the root, and you can make flour out of it, right? Out of certain ones. And the other one is vanilla beans, and they're the only edible fruit from the orchid. And finally, as we said, Melurine, some of the milk fat's been replaced by vegetable fat, right? Okay. So any questions so far? Right? So we also talked about vanilla, right? And we said vanilla comes from the tropics, right? Okay, so it needs lots of water and it needs lots of heat, right? So, I mean, from the equator to. So Tahiti and Mexico and Uganda and Madagascar probably has the most, right? Okay. And so it comes from this area. We said it's the second most expensive spice, right? And that once again, it's the only edible fruit from from an orchid. And we said the reason that it's so expensive is because everything has to be hand pollinated, right? So the reason that it's so expensive is everything has to be hand pollinated. And this isn't like uh, a climate change thing or anything. It's just that there's only one bee that can pollinate it, and the bees can't keep up with how much vanilla we want, right? Okay. So there's only one bee that can do it, and the reason is that the shape of the orchid, right? If you look at the shape, it needs a very small bee to get up into there, right? Okay. And then we said, so they have to be hand pollinated and then they're killed, right? And don't forget, killed means stuck in boiling water for a little bit. And then they're cured, right? And sweated to get rid of most of the moisture. And then they're shipped, right? So you've all worked with those vanilla beans, right? They start out looking like, like this, right? Okay. So they start out looking kind of like giant green beans or so any questions about that? Right, we also talked about the difference between artificial vanilla and vanilla extract, right? And we said that actually the chemical they're almost chemically equivalent, right? If you put them through a spectrometer, but they are, some people think they can tell the difference in the taste. And some people think you have to use twice as much, which means if it's half the price, that it's the same price. So any questions about that? Okay, then we talked about chocolate, right? Here, chocolate tasting. So we talked about chocolate, right? We said that it grows 10 degrees north and south of the equator, right? Which was kind of interesting. And we said there were 4 types, right? And we actually said that there's some physiological and psychological health benefits, right? So they actually can affect your mood, right? All right, we gotta even change this. Mood lifting, right? Okay. So in essence, they come off of trees that are shade that actually grow under other trees, right? So they have to be in the shade. And they get about 3 meters tall. You're about 2 meters tall, right? So about 1.5 times your size. And the pods form from the buds in about 75 days, right? And then inside you break them open and they're covered with this sweet mucilage white pulp, right? And we said it was interesting because sorry, wrong. They don't grow like apples, right? The pods can grow off the trunk, they can grow off the limbs, they just pop out of anywhere. Sorry, this is an old one. So we said the color depends on the source of the beans. So there's mainly 4 beans and you mix them together, right? To get the what you want. The degree of roasting. So all the beans have to be roasted, right? And then the fat content and the process, whether it's alkalized, natural or alkalized, right? What's another word for alkalized chocolate? Dutch chocolate, right? Okay. And the fineness of the grain and the amount of flavonoids that are in the chocolate already, right? So any questions about that, right? So it might be a couple of questions about chocolate. Um, then we started talking about how things work, right? Okay. I mean, how the plants work and how they operate. And before that, we talked about looking at how much energy there is in ice cream. So we said that ice cream was actually a pretty good food for like, especially old people and people that are sick, because most of the energy that it contains can be absorbed by your body and used, right? So that and there's lots of water and there's lots of things in there, right? So he said that in essence, um, in essence, I'm on the wrong one, sorry. So we talked about what a calorie was, right? And there were no questions on this, but we talked about what a calorie was. And that's just, if we take a chunk of the material and we burn it and we try to heat water with it, right? And we have a really good understanding of how water works, right? So we go ahead and 1 calorie is the heat required to raise 1 gram of water, 1 degree C, right? So you just burn the heck out of the food and try to get all of the possible energy out of it. And then you use it to heat water, and that's what we measured, right? And chemists use something called the calorimeter, right? So they'll just take the food stuff or whatever it is, and they'll just keep burning it, and it's surrounded in water, and they stir it to make sure that it's well stirred, and then they measure the temperature and see what happens, right? So that would be the absolute amount of energy there is, right? And we said that that comes out to be about 4.1 for carbohydrates, proteins about 5.6, and not fats about 9.45. That's not what we used, right? We used carbs were 4 calories per gram, and protein were 4 calories per gram, and fat was 9 calories per gram, right? Okay. And why didn't we use what the chemists found? Because that's what the chemists found, right? Why didn't we use that? Okay. Because our body doesn't work with like a calorimeter, right? Our body couldn't absorb all of the energy that it had, right? And we know that because, for instance, we have waste, right? Okay. So what we can absorb is about 4 and about 4 and about 9, right? And now and hopefully this shows you why you even have fat, right? Because you're usually trying to get rid of it. But the good thing is that it can store a lot of energy in a gram, right? Which means that if you need it, like if you're going to go hibernate or something, right? It'd be good to have, right? Is that okay? So that's what we used. All right, so I'll tell you, the extra credit question has to do with this, right? But there's no questions in the actual exam about that. But it does ask about these 3 things, right? Okay. So carbs are 4 calories per gram, and protein 4 calories per gram, and fat 9 calories per gram. So any questions about that? Right? Okay, so then we started talking about processes of making them, right? And we said the first thing we need, and the reason that ice cream prices went down, because it'd only be really, really rich people used to be able to eat it, is that we have refrigeration now, right? So that's a really important thing. And we said what happens with the refrigerator is that, and right, you should know how to draw this and tell what it means, right? So we have a refrigerator, it's a cold reservoir, right? So we have some cold reservoir, and we have some warm reservoir, right? And what we said was we're going to take a refrigerant and we're going to expand it so that it's low pressure. So we take the refrigerant and we expand it so it's low pressure and low temperature. And we mean the temperature is lower than inside the refrigerator. So we make it really cold. In which case, then we put it through some coils inside the refrigerator that you can't see, that are usually on the back of the refrigerator. And we just have them run through the refrigerator for a while, right? And what happens is that it absorbs heat from the cold reservoir, right? We said this is expensive and takes lots of energy, because what usually likes to happen is if we have a hot thing and cold thing, heat likes to move naturally from hot to cold. And we're trying to do the opposite. We're trying to take it heat from the cold and dump it out into the hot, right? So what we end up with here is a low pressure warm warm fluid, excuse me, refrigerant or fluid. Is that okay? So now what we're going to do is we'll compress it using an electric motor, and we put work or energy, so they're synonymous. So we get energy from our electric outlet, right? Okay. And we put it into here. So we had a low pressure warm fluid. Now I've compressed it. And we have a high pressure hot fluid. And by hot, I mean the temperature is greater than the temperature of the warm reservoir, which I forgot to label, right? So the temperature is greater than the temperature of the warm reservoir, right? And you know that pressure increases. Anybody that has a car that tells automatically your tire pressure, right? You know that as it gets hot, your tire pressures increase, right? Because you ever going on a cold day and all of a sudden there's all these alarms that your tires are all low, and you drive for a couple minutes and they warm up and suddenly everything's okay, right? Because your pressure, as the pressure increases, the fluid's going to get hot. And in your tires, the fluid is air. And don't forget, fluid means gas or liquid. And here, it's kind of a mixture of both. So, but so then what we do is pass it through more cables, coils, excuse me, not cables, coils that are outside the refrigerator. And if it's air conditioning, they're outside your house usually, right? And then we dump heat in to the cold reservoir. Excuse me, dump heat into the hot reservoir. And then we're left with a high pressure warm fluid, right? So a high pressure warm fluid. And then we continue the whole thing again. So in words, we expand a fluid, right? Through a valve. So we expand a fluid through a valve, right? And then it becomes a low pressure, really cold fluid, colder than the inside of the refrigerator. Then we run it through coils. And inside this cold refrigerator, it's going to accept heat, right? So the refrigerator is hotter than the coil. So it warms up the coil and cools down the refrigerator. Then we have a low pressure warm fluid, and we put it through a compressor. Sorry, I forgot the label compressor. Right? And we compress the gas. Now it gets hot. It's hotter than the outside of the refrigerator, and it exhausts the heat, right? Okay. And then we're left with a high pressure warm fluid, and we start the whole process over again. Is that okay? So any questions about that? Right. Then just one last thing, right? Okay. So one last thing, right? And it's the last thing that's on the test, right? Wait. So the very last thing is, what is pasteurization, right? Okay. So what's pasteurization? So don't forget, it's the process of heating every particle of milk or milk product to the minimum required temperature for a specific amount of time, right? So it's the process of heating every particle of milk or milk product to a minimum required temperature and holding it continuously for a minimum required time. I'm sorry, and the last thing is properly designated, designed, and operated machinery, right? So in equipment that is properly designed and operated, right? So what we're saying is you can't do it at home unless you buy a really expensive piece of equipment. I should say you can't do it at home with a pot and a thermometer. Anybody remember the two types? Yeah. What's the first one? Bat. Bat or batch, right? And what's the other one?
High temperature, short time.
So high temperature, short time. Which is too long to write, so we use HDSC, right? So batch usually used by smaller companies for smaller batches, right? High temperature, short time is usually used by larger factories, right? Or what's the word I'm looking, distributors or whatever you want to call them, right? And we said for ice cream, right? The vat is 30 minutes, which is a long time in manufacturing, right? At 155 degrees Fahrenheit. And this is 25 seconds at 180, oops, sorry, 175, excuse me. Okay, right? And we said that so the advantages I hope are pretty obvious, right? The high temperature short time is just takes less time and it's fast, right? It's just faster. The vat, since it's sitting there for 30 minutes, it could have like a cooked flavor after a while, right? Okay. So imagine heating your milk on your stove for 30 minutes. It's gonna change its texture and taste a little bit, right? So any questions about that? And the last thing we talked about was homogenization. And in simple words, right, we're trying to make it so that it stays homogenized the whole time, right? Okay. What we're going to do is take it and force the milk to move really, really fast, like through a nozzle, you know, like when you shorten, you know, like when you take your garden hose and you make the nozzles, you make the opening smaller, it has a higher pressure and shoots out faster, right? Okay. So we do the same thing, really high pressure, really high speed, and then just have it smack into a piece of metal. And then it breaks up the particles into smaller, breaks up the fat globules into smaller particles, right? Is that okay? And we said the whole reason this works is because the buoyant force, so the buoyant force is equal to the weight of fluid displaced. So the more fluid you push out of the way, the more it pushes up, right? So that's why we said, for instance, that's why ocean liners float. Because they push a whole bunch of water out of the way, even though they're really incredibly heavy. But if you crunch them into a ball, they wouldn't push as much water out of the way and they'd sink to the bottom, right? So in essence, it's creating a permanent homogeneous emulsion. So we're trying to mix two things that won't mix, fat and water. And we're trying to keep them well mixed, so there's not chunks of fat and water. Okay? So all we have to do is make the chunks of fat really small so that their buoyant force is really small. And then they just sit there in the milk. They don't sink and they don't float. Right? Any questions about that? Any questions about anything? And everybody knows when the exam is? When is it? May 1st? Thank you. Sorry, have I said that too much? Everything right? Okay.
Can you go back to that slide?
Oh, sure. Can I? Give me 1 second.